Hello everyone, good afternoon. My name is Subroto Debnath. My groupmate Kamrun and I will present Congestion, Avoidance and Control written by Jacobson. So let's start. This paper was published in 1988. So basically it's a paper of 34 years old. So why do we need to know about such an old paper? Is it that important? Yes, the paper is one of the basic pillars of today's TCP protocol. It redesigns the TCP congestion control algorithms. It saves the internet from collapsing in the late 90s to the early 80s. So its contribution was huge. Now let's move on the paper and talk about congestion. What is this? This picture depicts the congestion of traffic. We can see a lot of cars on the road, but the road is pretty narrow for those cars to move on. It creates traffic congestion. Now let's look at the network congestion. It creates when the load exceeds the capacity of the network. In this picture, we can see the server transfer data at 10 Mbps, but the router cannot handle that much data and only transfer 1.5 Mbps data at a time. So it creates overflow at the router queue, and when the queue is full, the packets are dropped. Now let's talk about the congestion problems. It occurred first in 1986 due to TCP retransmission. What really happened? According to old TCP rules, TCP protocol transmit data in full spectrum, but some data were lost in transmission and the rest remain in the queue. When the timer of the sender runs out, everything is resent. So why did this happen? The router was congested and the sender retransmit all data at once. At that time, this was standard for the TCP. The sole limitation on transmitting rate is the send window. At that time, the sending rate was equal to send window divided by the round trip time. Therefore, send window controls the sending rate. So, how can we mitigate the problem? At that time, send window was equal to the receiving window, but to mitigate the problem, sender should also address the network bandwidth. It will not send the total bandwidth it can be capable of. It will lower the sending window to reduce the rate of congestion. So, we need to add a congestion window, and send window will be the minimum value from the receive window and congestion window. Now let's talk about the conservation of packets principle. If the full window of data is in transit and the network is stable, only then we can say the network is in the equilibrium state. The flow of packets will be new is not put into the network until the old one leaves. There can be three potential issues with packet conservation. The first one is the connection doesn't get to equilibrium. And the second one is a sender injects a new packet before an old packet has exceeded. And the last one is the equilibrium cannot be reached because of resource limits along the path. So, how can we get equilibrium? It's easy. We will start slowly. This schematic representation of a sender and receiver on high bandwidth networks connected by a slower long haul net. The sender is just starting and has shipped a window's worth of packets back to back. The acknowledgement for the first of those packets is about to arrive back at the sender. The vertical direction is bandwidth and the horizontal direction is time. Each of the shaded box is a packet. So here, bandwidth into time equal to bits. So the area of each box is the packet size. If packets after the first burst are sent only in response to an acknowledgement, the sender's packet spacing will exactly match the packet time on the slowest link in this path. Now, let's talk about the slow start algorithm. We need to add a congestion window with receiving window. In the previous slide, we discussed why the send window needs to be the minimum value from the receive window and the congestion window. In the beginning, the value of congestion window will be 1. We increase the congestion window by 1 packet on each acknowledgement for new data. Now let's analyze the slow start algorithm. Here, slow is a mismode. The transmission rate expands exponentially. On each acknowledgement, 2 packets are sent. One for the packet acknowledgement, one for the increase of the window. So send window size double every round trip time. It takes R log 2 base W times, where R is the round trip time and W is the window size in packets. In this picture, we can see the difference between with and without slow start. Here, we may face congestion and possible data loss without a slow start. But using the slow start algorithm, we don't see any congestion, so there will be no possibility for data loss. Now let's talk about round trip timing. To keep a network in equilibrium, we need a good round trip time estimation. It should increase quickly with a load. That's all from my side. Now, my teammate Kamrun will continue the rest. Thank you everyone.
I'll talk about the congestion avoidance. Packet gets lost for two reasons. They are damaged in transit or the network is congested. And loss due to damage is rare, which is less than 1%. So it is probable that a packet loss is due to congestion in the network. A congestion avoidance strategy has two components. The network must be able to signal the transport endpoints that congestion is occurring or about to occur. And the endpoint must have a policy that decreases utilization if the signal is received and increases utilization if the signal is not received. Multiplicative decrease. If Li is the load at interval I, an uncongested network can be modeled by saying Li changes slowly compared to the sampling time. If the network is subject to congestion, this zeroth order model breaks down. The average queue length becomes the sum of two terms. The n accounts for the average arrival rate of new traffic and intrinsic delay, and a new term that accounts for the fraction of traffic left over from the last time interval and the effect of the last over traffic. So Li equal to n plus gamma Li minus 1. When the traffic is congested, gamma must be large and the queue length will start increasing exponentially. The system will stabilize only if the traffic sources throttle back at least as quickly as the queues are growing. Since a source control load in a window-based protocol by adjusting the size of the window W, sender policy on congestion Wi equal to d Wi minus 1, where d less than 1. A multiplicative decrease of the window size, which becomes an exponential decrease over time if the congestion persists. If there's no congestion, gamma must be near 0 and the load approximately constant. The network announces via a dropped packet when demand is excessive but says nothing if a connection is using less than its fair share. Suppose sharing the path with someone else and converge to a window that gives each one half the available bandwidth. If one shuts down, 50% of the bandwidth will be wasted unless another one's window size is increased. Additive increase. What should be the increase policy? The first thought is to use a symmetric multiplicative increase, possibly with a longer time constant, but it won't work. The result will oscillate wildly and on average deliver poor throughput. It has to do with the fact that it is easy to drive the net into saturation, but hard for the net to recover. Thus, overestimating the available bandwidth is costly. The best increase policy is to make small, constant changes to the window size. On no congestion, Wi equal to Wi minus 1 plus U, where U less than W max. W max is the pipe size. Take U equal to 1, so Wi equal to Wi minus 1 plus 1. Congestion avoidance algorithm. On any timeout, set congestion window to half the current window size. This is multiplicative decrease. On each ACK for new data, increase congestion window by 1 by congestion window. This is the additive increase. When sending, send the minimum of the receiver's advertised window and congestion window. Analysis based on sequence number. You can see on the picture no congestion avoidance. 4,000 out of 11,000 packets sent were retransmissions. The link data bandwidth is 25 kbps. Each of the 4 conversations should have received 6 kbps. Instead, one conversation got 8 kbps, 2 got 5 kbps, 1 got 0.5 kbps, and 6 kbps has vanished. With congestion avoidance picture, you can see 89 out of 8,281 packets sent were retransmissions. 2 of the conversation got 8 kbps and 2 got 4.5. The difference between high and low bandwidth senders was due to the receivers. The 4.5 kbps senders were talking to 4.3 BSD receivers, which would delay an act until 35% of the window was filled. This meant the sender would deliver burst of 5 to 7 packets on each ACK. The 8 kbps senders were talking to 4.3 BSD receiver, which would delay an act for at most 1 packet. The probability of loss increases rapidly with burst size, so senders talking to old style receivers saw 3 times the loss rate, which is 1.8% versus 0.5%. The higher loss rate meant more time spent in retransmit wait, and because of the congestion avoidance, smaller average window sizes. Analysis based on bandwidth. The thin line shows the total bandwidth used by the 4 senders without congestion avoidance, average over 5-second intervals and normalized to the 25 kbps link bandwidth. The sender sent on average 25% more than will fit in the wire. The thick line is the same data for the senders with congestion avoidance. The first 5-second interval is low because of the slow start. Then there is about 20% of damp oscillation as the congestion control regulator for each TCP finds the correct window size. The remaining time the senders run at a wire bandwidth. The average of total amount of data ACK per 5-second interval. The thin line is once again the old TCP. Only 75% of the link bandwidth is being used for the data. The thick line shows delivered bandwidth for the new TCPs. There is the same slow start and turn on transient followed by a long period of operation right at the link bandwidth. Combined algorithm, which is the combination of slow start and congestion avoidance. The sender keeps 2 state variables for congestion control: a congestion window, which is CWND, a threshold size. To switch between the 2 algorithms, the sender's output routine always sends the minimum of congestion window and the window advertised by the receiver. On timeout, half the current window size is recorded in threshold size. Then congestion window is set to 1 packet. When new data is added, you can see in the slow start, window opens exponentially. Otherwise, congestion avoidance increment by 1 by congestion window. So slow start open the window quickly to what congestion avoidance thinks is a possible operating point. Then congestion avoidance takes over and slowly increases the window size to prove for more bandwidth becoming available on the path. Thank you for listening.